Greetings, curious minds. Welcome to Frontier Obscura, where we dive deep into the bizarre, unravel the unknown, and shine a light on the shadows of science. Buckle up for a journey to the edges of human knowledge. Ladies and gentlemen, welcome to the cutting edge of artificial intelligence. Today, we're not just talking about making computers smarter, we're talking about giving them brains. Real, pulsing, synapse-firing brains. Welcome to the world of neuromorphic engineering, where science fiction becomes reality, and the future of AI is being written in silicon and light. Imagine a computer that thinks like you do, learns like you do, adapts like you do. A machine that doesn't just process information, but understands it, feels it, dreams about it. This isn't some far-off fantasy. It's happening right now in labs across the world, and it's called neuromorphic engineering. At its core, neuromorphic engineering is about building computers that work like brains. But why, you might ask, would we want to do that? Aren't our current computers powerful enough? Well, let's put it this way. The human brain is still the most sophisticated computing machine on the planet. It can process vast amounts of information in parallel, adapt to new situations on the fly, and do it all while consuming less power than a light bulb. Our most advanced supercomputers, on the other hand, guzzle electricity like there's no tomorrow and still can't match the brain's flexibility. Neuromorphic engineering aims to change that. By mimicking the structure and function of biological neural networks, we're creating a new generation of AI hardware that's more efficient, more adaptable, and potentially more intelligent than anything we've seen before. So how do we build a brain? Let's break it down. Memristors, the synapses of silicon. First up, we have memristors. These are like the synapses in your brain, the connections between neurons that strengthen or weaken based on experience. Memristors are resistors with memory. They can remember how much current has flowed through them in the past and adjust their resistance accordingly. This mimics the way our brains learn and form memories. Neuromorphic chips, the neurons of the future. Next, we have neuromorphic chips. These are the heart of neuromorphic systems. Unlike traditional computer chips, which process information sequentially, neuromorphic chips are designed to process information in parallel, just like our brains do. They're packed with simple processing units that mimic neurons, all interconnected in complex networks. Spike timing dependent plasticity, or STDP, is the learning algorithm. STDP is the secret sauce that allows neuromorphic systems to learn. It's a principle borrowed directly from neuroscience. In our brains, the timing of neural spikes influences how strong the connections between neurons become. STDP replicates this in silicon, allowing neuromorphic systems to learn and adapt in real time. Now, you might be thinking, this all sounds very impressive, but what can these brain-like computers actually do? Well, buckle up, because the potential applications are mind-blowing. Energy efficiency, green AI. Neuromorphic systems are incredibly energy efficient. While traditional AI systems guzzle electricity, neuromorphic chips sip it. We're talking about AI that could run on a smartphone battery for days or even weeks. This isn't just good for your electric bill, it's crucial for developing sustainable AI technologies that won't contribute to climate change. Imagine an AI that can learn and adapt in real time, just like you do. That's what neuromorphic systems offer. They don't need to be taken offline and retrained every time they encounter something new. They can learn on the fly, making them ideal for applications like autonomous vehicles that need to adapt to unpredictable real-world situations. Our brains are amazing at recognizing patterns, even in noisy or incomplete data. Neuromorphic systems bring this ability to machines. This could revolutionize everything from medical diagnosis, spotting subtle signs of disease in scans, to weather prediction, identifying complex patterns in climate data. Language is one of the most complex tasks our brains perform. Neuromorphic systems could lead to AI that truly understands language, not just in terms of words and grammar, but context, tone, and even emotion. We're talking about machines that could engage in natural conversation, understand nuance and sarcasm, maybe even appreciate poetry. Let's look at some real-world examples of neuromorphic engineering in action. Intel's Loihi, the self-learning chip. Intel's Loihi chip is a neuromorphic marvel. It can learn and adapt in real time, solving complex optimization problems faster and more efficiently than traditional computers. In one experiment, it learned to smell dangerous chemicals, opening up possibilities for applications in security and environmental monitoring. IBM's True North, a brain on a chip. IBM's True North chip packs 1 million neurons and 256 million synapses onto a chip the size of a postage stamp. It can recognize objects in real time while consuming less power than a hearing aid. Imagine the possibilities for augmented reality, robotics, and smart sensors. BrainScales, Europe's brain-inspired supercomputer. The BrainScales project in Europe is building a supercomputer that operates 10,000 times faster than a biological brain. It's not just about speed, though. This system aims to replicate the brain's ability to learn and adapt, potentially leading to breakthroughs in our understanding of cognition and new treatments for brain disorders. Now, let's talk about the elephant in the room, the potential for neuromorphic engineering to lead to superintelligent AI, often referred to as the technological singularity. Neuromorphic systems bring us closer to creating AI that thinks like humans do. This could be a crucial step towards artificial general intelligence, AI that can perform any intellectual task that a human can. From there, the path to superintelligence, AI that surpasses human cognitive abilities, becomes clearer. However, it's important to note that we're still a long way from this scenario. Current neuromorphic systems, while impressive, are still far less complex than the human brain. We're talking about chips with millions of neurons, while the human brain has billions. That said, the rapid progress in this field is both exciting and slightly unnerving. As we create AI systems that more closely mimic human cognition, we'll need to grapple with profound ethical questions. How do we ensure these systems align with human values? How do we prevent them from being misused? These are questions we need to start answering now as the technology races ahead. But the future is bright. We're seeing the development of new neuromorphic devices, like nanoscale synapses that bring us even closer to replicating the brain's incredible efficiency. We're exploring hybrid systems that combine the best of neuromorphic and traditional computing, and we're drawing ever more inspiration from neuroscience, developing algorithms that mimic not just individual neurons, but entire brain regions. One thing is clear, the future of AI is going to look a lot more, well, human. We're moving from computers that merely calculate to machines that think, learn, and maybe even feel. Neuromorphic engineering isn't just about making better computers. It's about understanding ourselves, unraveling the mysteries of cognition, and potentially creating new forms of intelligence that could help us solve some of humanity's greatest challenges. And if you like this episode, be sure to like, subscribe, and share this video with a friend.